Hello everyone. On behalf of Indian National Trust for Art and Cultural Heritage INTACH and the INTACH Conservation Institutes, I extend a very warm welcome to our distinguished speaker, Dr. Chiara Pasian, and everyone who has joined us for today's talk in the Conservation Insights 2020 lecture series. I'm Dr. Padma Ruhila, Director ICI Delhi. Now to introduce our speaker, Dr. Chiara Pasian is a wall painting conservator and currently lecturer in the Department of Conservation and Built Heritage at the University of Malta, where she teaches the MSc course in the conservation of decorative architectural surfaces and supervises students in field projects. Pasian is strongly interested in applied scientific research and holds a PhD from the Courtauld Institute of Art, London. Before joining the University of Malta, she had been a visiting lecturer at the University of Applied Sciences and Arts of Southern Switzerland, SUPSI, and at the University of Tsukuba, Japan. She is currently a member of international committees related to conservation, including assistant coordinator of the ICOMCC Mural, Stone, and Rock Art Working Group, and member of the RILEM Technical Committee specifications for testing and evaluation of lime-based repair materials for historic structures. Besides academic research, she also works as an on-site conservator. She has been involved in projects in collaboration with different private and academic institutions such as University of Brescia, Italy, and the Courtauld Institute of Art, London, in several countries, including Malta, Italy, Switzerland, France, Turkey, and India. The title for today's talk is Injection Grouting for Delaminated Wall Paintings, Approaches, Design Challenges. Wall paintings are complex porous systems, typically composed of several layers. Such layers may suffer from lack of adhesion, potentially resulting in delamination between support and plaster and or between plaster layers. When severe, such a phenomena can lead to the total loss of the painting. While in the past, conservators used to detach wall paintings undergoing delamination to avoid their collapse, this practice is now rarely used, and that stabilization on site is preferred. Such stabilization is undertaken through injection grouting, introducing in the delamination a compatible adhesive material with bulking properties. The injection grout should tailor the specific case under consideration. Starting from setting the performance criteria for the intervention, the grout is designed and undergoes testing both in the field and in the laboratory until satisfactory for implementation. This involves large amounts of water, potentially detrimental for organic water-sensitive materials and problematic in case of contamination with soluble salts. Recently, injection grouts with reduced water content were designed and studied in order to limit the amount of water involved in the intervention and the problems mentioned above. This will be discussed today. So before I invite Chiara, may I please request all of you to mute your microphones and please type in your name, organization name, and email address in the chat box. We'd love to know all of those who have joined us. And also type in the questions there. We'll be taking those up at the end of the lecture. So Chiara, thank you so much for accepting the invitation and for this talk. Over to you.
Thank you very much, Padma, actually, for inviting me. That's a real pleasure. So thanks a lot. Good. So as Padma anticipated today, I'm going to talk about injection grouting for wall paintings. And before starting, as we're talking about wall paintings, I'd like to introduce first decorative architectural surfaces. So what's a decorative architectural surface? It's any decoration for which the support is a structure itself. And this is definitely one of the main peculiarities of this kind of work of art compared to others such as canvas paintings or objects. So what is really the main characteristic they have is that they are immovable. So they are bound to the structure of the building they're part of. And therefore they have indeed an immovable support or structure. And what about wall paintings? Decorative architectural surfaces can include indeed wall paintings, stuccos, reliefs, mosaic. Wall paintings in particular, as are mosaics, for example, and also stuccos and this kind of work of arts, are multi-layer systems. So they're complex, not just topographically speaking, but also stratigraphically speaking. And they can have just few layers in their structure. So they can have a minimum component of just support and paint layer, but they can also be extremely layered and extremely complex. And they can have primary support, secondary supports, including plaster layers. They can have a number of preparatory layers, several paint layers, and so on. So they're extremely complex stratigraphically. And as we will see now, the peculiarity they have is that they are at the interface with a physical open system. So what does it mean? As they are immovable objects being part of a building, they can't be, of course, as you can imagine, be placed in a safe environment in a museum with controlled RH, controlled temperature, which are ideal for their conservation. They are just in the environment. And so, as I said, as they are extremely complex and also heterogeneous, both topographically and stratigraphically, if we take a tiny piece of a wall painting, a tiny sample, and we make a cross section of it, and so we can see its stratigraphy in detail, we can see that there are multiple layers indeed, as I said, and multiple interfaces. And we need to think that all these materials throughout the stratigraphy are interconnected, and they are connected and at the interface with the environment on one side, so on the external part, and they are connected, of course, also to the porous support they lay on. And there is a constant exchange throughout all these layers with the environment itself. So there is passage of liquid and gas. And therefore, when we face the conservation of such works of art, of course, this is a major challenge in the work we face. Another peculiarity of wall paintings compared, for example, to other objects, it's their scale. So not always, of course, but very often they are vast surfaces. So we need to think that the challenge is to find an approach, a conservation strategy, which takes into account not just the single portion of the painting, which may have a problem we want to tackle, but of course, all the cycle of painting, all the sites. And an example I like to show is this one. This is Virgin with Child, which is located in the Tokali Kilise in Göreme in Cappadocia in Turkey. It's a beautiful painting, which is more or less this size. But we need to take into account that this painting is part of this rather big church, which is indeed the Tokali Kilise, which has different painting cycles according to different periods. And this beautiful church is actually carved into the rock. So this is the external part of the church. So it's part, again, of a more complex and wider context. And in turn, this church is just one of many rock churches which are found in this amazing site, which is now the Göreme Open Air Museum. So when we face the conservation of a wall painting, we need definitely to take into consideration the big context and what the work we do on just a portion of it can mean for the conservation and also the management of all the rest. So what are indeed the challenging of conserving wall paintings, just to summarize some of them? As we said, they are extremely heterogeneous and vast potentially surfaces. The decorative surfaces are at the interface with the physical open system. So they face environmental changes and everything is connected through the porous materials. And very often the causes of degradation cannot be removed because they are part of the physical open system, they're part of the building the wall paint is connected to. So they cannot be removed, and we need to find solution in order to minimize them. So now we put in context wall paintings. Let's see what we're going to talk about today. So injection grouting aims to address delamination, so a particular problem wall paintings can have. So what's a delamination? A delamination, when there is a delamination, there is a loss of adhesion at the interface between layers. So when I'm talking about adhesion, I'm not talking about cohesion. So there are two different things. So let's try to differentiate them. So when I have a loss of adhesion, I have two separate cohesive layers that are not bound at the interface anymore. So for example, here in the picture, we can have, I hope you can see my mouse. So you have three different layers. You have this one, where is it? Here. This one, which is the support, another layer here, and another layer here. And they're cohesive, meaning that the particles forming them are well bound together. So they're strongly bound together. However, as you can see here, there is a loss of adhesion, meaning that there is a little gap at the interface. On the other hand, loss of cohesion means that the particles of one single layer are not bound together anymore. And so you have, for example, here, a powdery paint layer or a powdery plaster, a powdery surface. So we're gonna talk about adhesion today. So in a delamination, you have indeed loss of adhesion at the interface between either support and plaster, or for instance, plaster and plaster. And so you can see here an example. And what is quite dangerous about it is that when it's highly unstable, such as in this case, for example, you risk basically the total loss of the painting. Injection grouting is a remedial intervention that can potentially save the paintings. So what's the aim of it, indeed? So injection grouting aims to address a failure of adhesion between layers. We saw that. How? Introducing a compatible adhesive materials, which also has bulking properties. So it's able to fill this gap, which is between different layers. And why is actually quite important injection grouting in some cases. It's a stabilization intervention for paintings at risk of collapse, as we have seen in the other picture, potentially. And because we know, sadly, that past interventions have been unsuccessful or inappropriate. So for example, detachment might have been successful, meaning that the conservators were actually able to detach the wall painting. But of course, the nature of wall painting is to be bound to the building itself. So is a change of nature of it, let's say. Or in the past, the different materials were injected, such as resin, which have a different physical mechanical behavior, and so can put the wall painting itself in danger. So not very really recently, but in the last decades, I think that conservators mainly agree that injection grouting, if possible, it's actually a more appropriate intervention in case of delaminated wall painting. It is actually rather complex very often, as conservators of wall paintings, I'm sure, know. Why? Because as we can see from these pictures, often wall paintings that actually need injection grouting are in an extremely fragile condition. So we can see, for example, this very bulky delamination here, and it is clear that this is really unstable and fragile. On the other hand, the assessment of the intervention of the delamination first and of the intervention itself presents some difficulties. Why? Because very often it is concealed, so you can't really see it. So in this extreme case, you can actually see the delamination and what's behind it. But often it's not this clear, and is actually, there are not many access points, or there are not cracks such as this one. So it's actually quite difficult to see and to assess. And because it's concealed indeed, very often it's quite inaccurate as an intervention, because there are indeed some instruments which we can use in order to help the intervention and to try to understand where the delamination is, where the grout is going, but still we can't see it clearly. So the assessment is quite difficult, and it is inaccurate. And also, this is a very important point. The grout, when injected and when it's set, actually becomes a permanent part of the wall painting. So grouting is not reversible. You can't inject an injection grout and then remove it years after if, for example, the intervention was not appropriate, or if it failed. It's behind the layers. And so the only thing we can do is to retreat it, so to intervene again. But we can't really take out the grout from the painting, from the stratigraphy anymore. So what do we do in practice? We have an injection grout, which is a fluid material, as we will see later. We'll see its composition. And the grout is injected through syringes to which a catheter is applied, or a needle, according to the access point, of course, the delamination type, and also the type of grout. So these grouts are injected behind the plaster, and they are supposed to indeed fill the gap and re-adhere the layers which had this loss of adhesion, and in between which there was a pocket. So what's the composition of an injection grout? So we have always a binder, which is indeed binding everything together. We can have aggregates of different types, of different granulometry. We'll see later this in more detail. We may have additives, not always, not necessarily. As we'll see, it's according really to our needs. And we always have a suspension medium, which is typically water. And so it's a liquid, which indeed keeps in suspension all these components. And I underline it's a suspension indeed, because we might be led to think it's a solution, but actually, no, we're talking about a suspension. So we have particles, aggregates, binder particles suspended in this liquid. So what's the function of these different components? The binder, as we said, binds indeed all the components when the grout is set, and results in the matrix of the grout at the end. Aggregates give the bulk and may help reducing shrinkage or increasing flow. So we'll see that according to the aggregates, which are coupled and chosen according to the particle size, to the shape, we may be able to achieve different properties. But indeed, aggregates are always needed in an injection grout. Sometimes additives may be used to do what? So to, let's say, modify different grout properties and improve them, basically. So you can have, for example, plasticizers to improve injectability, adhesive to improve adhesion, air entrainers to increase porosity, and so on. So again, they're not always necessary, but they may help according to the question we have. And then, as I said, a suspension medium, which allows the grout to be liquid and injectable and keeps the components in suspension. So some example, binder, we can have lime, which can be slaked lime, hydrated lime, we can have hydraulic lime, we can have earth, we can have gypsum. So different kind of binders according to the original materials. We can have, in terms of aggregates, inert fillers or pozzolanic fillers. They will give to the suspension and then to dissect grout different properties, and also will lead to different chemical reactions. And we can have additives which are synthetic or natural. And as I mentioned before, we can have various types of fluidizers, air entrainers, and so on. The suspension medium is typically water. And of course, as wall paintings very often face problems of soluble salts, typically deionized water is used. So what do we say about injection grouts? That we would like them as similar as possible to the original materials to stabilize in terms of performance characteristics. So what does this mean? In general, so meaning for any grout, we would like minimal grout volume change on setting. Why? Because we're trying to re-adhere two different layers at the interface, and it depends on the lamination, but often to fill a gap, to fill a pocket. So of course, if we inject something that then shrinks, we basically defeat the purpose. So the two different layers will not adhere anymore. So we always want minimal grout volume change in setting. We know that wall paintings are, I would say, always very porous system or porous systems. So we want porosity and related properties, so water vapor permeability, capillary water absorption, which are similar to those of original materials, and other properties such as mechanical strength, similar to that of the original materials or less. We don't want something which is much stronger than what our original materials are. And how do we achieve this? So what do? We do an analysis of original materials, and with such information, we can have an idea of the grout components we might want. And it would be ideal, but is not always possible. It's rather difficult. It would be ideal to know the original material's properties, so that with such information, we can also tailor what properties we want from a grout. So what's the approach to this rather complex problem? Well, we start indeed, as I anticipated, and it's always the case in a conservation project. We start with the study of the original materials and with the definition of the problem. So what is the problem we're facing, and how can we define the grout performance criteria? So once we understand what's the problem, how can we tackle it? We need to have very clear in mind how we want our grout to behave, basically. And so in terms of study of the original materials, of course, we start with the observation of the stratigraphy in areas of losses, for example, or where actually the delamination is, if it's not concealed. We can use a portable microscope in order to look at the plaster, for instance, and to appreciate the size of the aggregates, to see if there are some inclusions. For example, this is a plaster in Malta with some local aggregates and with the presence of some shells. We can do microchemical tests in order to understand what the binder is, if that is not really clear, for example, lime or gypsum. And of course, and that's very good, but not always possible. We can do a thin section, for example, of the plaster. And like this, we have the opportunity to see how the porosity is, the matrix, the different aggregates, and how many aggregates are there in, of course, this reduced sample area, what's the shape, what's the quality of them. So study of the original materials in order to understand what's the original technique in terms of plaster I'm talking about here, and support. And then indeed, we need to analyze what is the problem we're facing. So we can have, of course, a huge variety, infinite variety of delaminations. We can have, for instance, very thick ones with a deformed surface on a vertical surface. We can have very thin one with a small crackler and a very thin gap between layers. We can have an horizontal one, so on a ceiling or on a vault. And so we can have very actually different problems. So vertical versus horizontal, that will change things in terms of grout design. We can have delamination between layers of different materials. So indeed, we can have plaster, support plaster. Of course, the plaster may change even in the same site. And also we can have, of course, different thicknesses. We can have a deformed surface or not deformed. And so the question is, can I solve it just with one material? I guess you will think, no, I can't, because these are such different problems that it can't exist just one perfect material to tackle all of this. So what I need to think is, what are my requirements? So what are my performance criteria for the intervention? And so I have general criteria, so criteria which should be always valid for a grouting intervention. And then we'll see, we'll have also site-specific criteria. So in terms of general criteria, what do I need from a grout? As we said, we want minimum volume change in setting, we want porosity and water vapor permeability, which are similar. Mechanical strength, we say we would like it similar or less, because we don't want a repair material which is too strong compared to the original ones. And then what we need, good cohesion, of course. We don't want something powdery behind our painting. We want a good adhesion, because that's the purpose of it. So we need to re-adhere different layers. So good adhesion is fundamental. And also in terms of properties of the material when injected in the fluid state, we need adequate injectability, otherwise we can't perform the intervention, and adequate flow and viscosity. So this is in general always needed. However, sorry, this first. So we have this general criteria, which I mentioned, which concern the material either when it's still in the fluid state. So they regard the material during the intervention. So they're called working properties. And we have properties of the grout, which are called set grout performance, which concern the material after it's set. So when it becomes hard, basically, and it's supposed to stabilize the whole system. So in terms of working properties, we have adequate injectability and flow, adequate viscosity, and minimum shrinking volume change in setting. In terms of performance criteria, we have indeed everything which concern the material when in a hard state. So we mentioned porosity, mechanical strength, cohesion, and adhesion. So we need to have these two categories in mind when we design a grout and we go through testing, as we will see. So general criteria for every grout, but as I said before, of course, we need site-specific also criteria. What does it mean site-specific? Which tackle the specific problem we are facing in that particular site. So for instance, do I have a horizontal delamination? In that case, very likely I will need some light material, so something having low wet and dry density. Or do I have a particular severe problem with soluble salts? There is a high contamination, soluble salts. I will need, for instance, a low water content in my grout. Do I have a very thin delamination? Well, in that case, of course, and you can imagine, I have a very thin gap, and so I need a grout which is very fluid. So I will need a very good injectability and a very good flow. So as you can imagine, every case is different. And so every time I need to set basically these site-specific performance criteria to lead the formulation of the grout in the, let's say, right direction. So what now? We studied the original materials, defined the problem, defined the performance criteria. Now, indeed, we need to formulate the grout. And so we need to select the components, we need to decide the ratios. And so how do we start? I'd like to point out first that we have basically two possibilities. We can use premixed injection grouts, and we can design our grout with separate components. So today I will talk about grouts with separate components, but let's see for a moment what are these premixed injection grouts. So they're typically hydraulic lime based, so that's the binder. Of course, then if you have a different binder in terms of original materials, that's a different story. But talking about lime-based plasters, these may be used. So why hydraulic lime? Because the delamination is behind, basically the paint layer is behind the plaster or in between the plaster and the support. And therefore the CO2 axis is limited. So it's not in direct contact with the air very often. And therefore carbonation may be actually very slow to occur or difficult to occur. So premixed grout very often are not lime-based, but they are hydraulic lime based because the reaction indeed is hydraulic. So for the reaction to happen, you just need water. So that's the reason, just easier to happen. And such premixed grout, how do you find them? They're basically a powder in which all components are already mixed together, and you just need to add water to it. So it's very easy and therefore very tempting to use because it's easy to use, it's very quick, it's already tested by the manufacturer. And very often there is presence of additives. I would say in all premixed grouts, there is presence of additives. So there are, for example, air entrainers, plasticizers very often to make it very injectable. So that sounds all very appealing and easy and good to do. However, there may be some problems. So I'm not saying that these are always better to use, but we need to take into consideration that there are some problems. So for instance, the composition is unknown. So you have a description on the technical data sheet, but it's rather vague very often. And I would say as very often in general with conservation materials, you buy the exact composition is not disclosed basically. They are premixed, so they're always like that. So what does it mean? That they do not tailor the case under consideration. You just have a standard material. You can choose among others, that is true, but it's a standard material that to apply to potentially very different cases. And this is very important. They may have unsuitable properties. So for instance, as they're hydraulic lime based, quite often, not always, but quite often they may have a too high mechanical strength compared to the original materials. So we need to be very careful about these things and take them into consideration. So I will talk today about grouts with different, separate components. So for this reason, we can talk about formulation of the grout. So we mix it, we choose it, we do it. So in terms of selection of components and their ratios. So we said that we do this keeping in mind what the original materials are, what's the stratigraphy, what's the composition. According to this, we may have a lead to choose a particular binder and particular fillers aggregates. And usually you try to start simple, meaning that you don't try to overcomplicate immediately your formulation. And then according to performance criteria, I think, do I need something more? Do I need some additives? And during the rationale of the formulation of the grout, I need to think, how do I obtain the properties I want according to my performance criteria, balancing the grout composition, because it's not easy indeed. So I need to think about working properties, we said, and so I need to think about the rheology of my material. So what's the behavior of the material when liquid? And I need to think, of course, about the performance characteristics. So about the set grout performance. And so I need to think about my hard material in terms of packing density and geometry. So what's the appearance, microscopically speaking, in terms of how the different particles bound together when my grout is set. So in order to try to control rheology and packing density and geometry, I need to think about particles. So the particles of the binder and of the fillers of the aggregates my grout is composed of. Reminding you, indeed, the injection grouts are suspensions. So particles are involved in this and play a key role. So what about rheology? So working properties when I inject my grout and it's still in the fluid state. So thinking about particles and therefore aggregate in particular, more than binder in this case, I have different variables I can adjust. One of them for sure, and the main one I would say, is the volume fraction. So it means the amount of solid I have in the suspension, how many aggregates I put, what's the amount of them I put, because that will hugely change things. Another very important factor is the particle shape. So as you can imagine, I can have very round spherical particles, I can have irregular ones, and that will definitely change the behavior of my material in the liquid state, my rheology. And also what's the sphericity of them, are they angular? So different aggregates, as you know, also when we prepare plasters, impart different properties in the fresh state, but also in the hardened state. So this is an example. This is a grout. It's an SEM image, so scanning electron microscope image, and it's a broken section. So it means it's a sample and it's not embedded in resin and cut to make a cross section, but it's the piece, let's say, as it is. So we can appreciate the 3D structure of it. And you can see that we have spherical particles, we have angular particles of different sizes. So these will definitely have an influence on the grout properties. On the other hand, the particle shape, indeed, we also have an influence when the grout is flowing, clearly. So even intuitively, we can imagine that a spherical particle, when flowing together with all the others in the grout, will make, let's say, less of an effort to roll flowing compared to an elongated one. And also the particle size distribution. So in terms of particle size and how the different aggregates are distributed in terms of granulometry will have an influence on rheology. So if we have, for example, two types of particles with a different size, so to simplify, I've put some big orange particles and blue small particles, we can see, for instance, that in terms of viscosity, so how thick, let's say, the grout is and how easily it flows, if we have a mixture of particle size, the resulting suspension is less viscous. So in terms of viscosity, to give you an idea, water is basically non-viscous, so it's very liquid, let's say. while on the other hand, a very viscous substance can be ketchup, for example. So this I'm talking about in terms of viscosity. So we can see that when we have different particle sizes coupled together, the viscosity of the grout is lower, and therefore the flow can be better. Another factor in terms of controlling the rheology in terms of particle is the water absorption of them. So you know by experience for sure that there are some aggregates which are more porous than others. So for example, if we have particles of bricks, we know that they absorb water more compared to, for instance, marble dust. And so as they are porous and they are part of the suspension, if they are very porous, they may absorb already the water which is part of the suspension medium, and therefore they may have an influence on how the grout is behaving, biologically speaking. What about particles in terms of packing density and geometry? So how about particles when we have the set grout? Also in this case, if we consider, let's say, a space we need to fill with some aggregates, we can see that if we have aggregates which are of this shape, so particularly angular, but all of the same size, we have a certain degree of packing. So we can see that we have still some empty spaces. If we couple aggregates of the same type with different particle size, so we have, for example, big one, but also small one, we can see that the packing is actually better. So of course, there are still spaces which are left, and this is normal. But the packing density is much better and much more efficient. And the same happens if we have particles which are round. So here we can see the space filled just with particles of the same size. And here we can see particles of different sizes. And you can see again that in this case, the packing density is more efficient. What's the best in terms of packing density and geometry? The best is when we have different particle size, but also different particle shape. So when we put together aggregates which are round, but also angular or different sizes, we have a very good and efficient use of the space, let's say. And this is a real example. This is a grout. It's again a SEM image, but this is a cross-section. So the sample is embedded in resin, cut, and then observed in cross-section. And we can see indeed that this is all very dense, so it's all very nicely packed. And we can see indeed that we have particles of different shape and different size. And basically all spaces are filled. There is still porosity, of course, macro porosity, micro porosity, but this is going to be a grout with very good cohesion because everything is well packed. So if we have an efficient packing density and geometry, we will have less shrinkage. So in terms of shrinkage, this will be beneficial, even if this is mostly affected by volume fraction, so by how many aggregates I have in my grout. Cohesion, which in turn has an influence on mechanical strength. Porosity, so this will have an influence on porosity, which in turn will have an influence on mechanical strength and other properties which are related, such as the passage of water and liquid water and water vapor. So basically it's on particles, and yeah, that's extremely important in grout design. So after the formulation of the grout, what shall we do? Presumably we will have different options, not just one. So how can we decide about them? Well, we need to test them in order to understand what their properties are. So we go with the first stage of testing, physicochemical properties, which we consider paramount, and now we will see, because it's the first part. So I really need to decide what is to retain and investigate further and what's to discard. So I have the first stage of testing. I assess the properties in order to understand if the grout design is suitable. If it's not suitable, what do? I just go back. I just go back to formulation of the grout. Something was wrong, so I need to adjust my formulation. And then I go back and I test it again. So it's an iterative process. I go back and forward. If the grout actually is suitable, good. So I can go to the second stage of testing. So I can test the properties which are more difficult to test, or which involve some lab testing, for example. And again, I assess if the properties are suitable. They are not, I just need to go back to formulation. If they are suitable, I can go with implementation. So why all this testing, which is rather long and often complicated? So why is it important? Well, we said that grouting is not reversible, it's only retreatable. So we really don't want to have something which is part of the stratigraphy, which is not adequate. We can't remove it. And so we absolutely need to know what are the performance characteristics of the grout. And we want it to be compatible with original materials, with original plasters, of course, in terms of composition and properties and physical mechanical behavior. And in terms of working properties as well, very important to test. Why? Because we want to be sure it is suitable for the specific problem. So, for example, it needs to reach the delamination to stabilize. If it doesn't flow enough and doesn't reach, my intervention is pointless. Or I want it to be viscous enough to stay in place. Maybe I don't want something very liquid. So still very important to test working properties. And the important thing I need to point out is that testing is also performed during the design process, because changes in components proportion may change properties. So if I say, I'm just going to put a bit more of sand, well, that would change everything. So I need to test again. Or I'd like a bit more water to make it more injectable. Well, it's not just injectability, everything else will change. So this is an ongoing process during the design. Of course, I can have different degrees of testing. I can have qualitative testing, which gives me a non-numerical datum. It's easier to do. I can do it in the field, but still can be very informative and useful. It can give me information about the feasibility. So this is a material which potentially I can use. If so, maybe I want to test it further, but let's see first if it's feasible. And it definitely can be useful for a comparison among different possibilities, among different grouts. So for example, this is a very simple shrinkage test. So these are plaster cups filled with grout. And here we are assessing shrinkage. So we're excavating the grout and look at interface. And you can see here that there is no shrinkage because the adhesion is good, while here there is shrinkage. So this is very simple. It's definitely not giving a numerical datum, but it's still very informative. And of course, then I can have testing, which is far more precise and is quantitative. So it gives me a number at the end. It's very precise indeed. So you do it usually in the lab, but not necessarily. And there are also different standards potentially we can use, which are documents defining the procedure and the characteristics of a product. So according to different countries, you can have different lab standards. And the same property can be tested in both ways. And again, it really depends what kind of information you need. So this is, for example, injectability. You can just do it like this with, for instance, different catheters applied on your syringe. Or you can do a lab test, which is called column test, which requires, of course, some equipment. So you wouldn't do this on the field. But this can be already informative indeed. It depends on what you need. This is flow. So you have here a flow cone, so a test you do in the lab, or you can have on site just a very simple plaster tile, reproducing the original plaster, and you can just see different grouts and how they flow on this plaster. So this is the field version of that one. Or you can have this one, for example, which is concerning bleeding. So how much the solid and the liquid of the grout divide one from the other. So again, you have the lab version with a graduated cylinder, or the field test version just with a syringe with the tip blocked. Or for example, this test of adhesion, this is the laboratory version involving mechanical testing machine, so giving you a very specific number in terms of adhesive strength, or the field version with the preparation of the sandwich, and the assessment is still a quantitative assessment because you calculate the strength according to the surface and the weight you add, but still, of course, is far less precise. So talking about field testing, so starting simple, even if you're in your lab, but starting simple in order to assess if a grout is broadly promising or not. What tests to carry out first, which can give us an idea of how a grout can perform? Of course, this is not a rule, but this is what I feel it's mostly useful to know at the beginning, where for sure shrinkage, because if a grout shrinks, it doesn't work. And that will also influence adhesion. Flow, it's important because we need to inject it. Very often wet and dry density is important, particularly if it's a horizontal surface. So if you're working on a vault or on a ceiling. And also porosity is very important because we want it to be porous enough to be compatible from that point of view with the original materials. Porosity, however, is often a quite complicated test to perform. So on the field, we usually do capillary water absorption tests. And what other properties we might want to test? Of course, that depends on our specific problem. But these are a few examples. So for example, if there are salt problems, we might want to test water release, so desorption of the grout. If it's a grout with a lot of suspension medium, because we want something very fluid, we might want to test bleeding. And of course, adhesion is quite important to test. And usually it's more useful to test more simple properties at the beginning, and then going to adhesion, which is more complex to test. And then what? So we have this basic field test. We select some grouts which are promising and look like they behave in a good way. Then, of course, we can do a proper testing in the lab if it's needed, or for properties which are particularly important according to our performance criteria, site-specific performance criteria. So we might want to test water vapor permeability, we might want to test the more in-depth mechanical strength, and so on. This is a book I can suggest to you, which is very good. It's a Getty publication, and it's indeed about testing injection grout. And there is a very nice division between lab testing, but also more simple field testing. And in addition to this, there is this RILEM technical committee, which is on specification for testing and evaluation of lime materials, including grouts, which was set up because actually there are no international standards which are agreed on this topic. So not for grouts. There are standards for grouts used for, engineering projects. So basically structural grouts, but not grouts for decorated surfaces or non-structural grouts. So this is a very good starting point because it takes that into consideration. And this committee is trying to give recommendations so that also international standards shared in different countries can really tackle this kind of materials for cultural heritage. So in terms of complexity of the intervention and possible problems which grouting can lead to, as we saw, the typical suspension medium of grouts is water. And in general, the whole intervention involves a large amount of water, typically, because in order to, before injecting the grout, usually pre-wetting is performed. So the pocket is pre-wetted with water or water and alcohol in order to prepare the surface so that the plaster doesn't absorb immediately all the suspension medium of the grout, which would shrink immediately. And then, of course, a lot of water comes in with the grouting itself because it's the main component in terms of amount of the grout. And so we do know that water plays a role in the setting and hardening process in the chemical reactions. But an excess of water may lead to segregation, bleeding, shrinkage of the grout. And also in the wall, what can happen? So for sure, there is an increase in water in the porous structure, and then it's very difficult that the water will leave, basically, will completely evaporate. It's a problem if there are water-sensitive materials. And in case of soluble salts, that will lead to their stabilization, diffusion, and recrystallization with all the mechanical damage which this can entail. So from this, the need was felt in terms of research of water-reduced injection grouts. So injection grouts designed with a low amount of water. So why? Mainly to limit the solubilization and diffusion of soluble salts in contaminated plasters, but of course also in case of water-sensitive materials. So in this research, reduction of water was evaluated in grouts. And of course, it needed to be verified that grouts' intrinsic properties, so both working properties and performance characteristics, were suitable for implementation on site. I'm saying here generally because this was studied not for a specific case study, but as a laboratory study. So we know that there are some chemicals such as plasticizers, superplasticizers, which allow a strong water reduction and they lead to a very good injectability. So why not using those directly? Easy. Well, there are some problems because if water reduction is massive, there is a strong reduction in porosity. And as a consequence, there is an increase in mechanical strength. And so this research tried to reduce water, avoiding this kind of chemicals. Also, very often these chemicals are soluble salts forming. So that kind of defeat the purpose. So they were not used. So how was water reduction achieved? Ethanol, so alcohol, was investigated as partial substitute to water during grout preparation. Why ethanol? Because it's a less effective solvent for ionic substances, so for soluble salts, in comparison to water, and that was studied in the past. During this research, lime pozzolan grouts were considered. So we know that in a lime pozzolan material, two main reactions are involved, which are carbonation and hydration reactions. And so it needed to be understood what was the role of water in those. So basically, it needed to be understood what's the minimum amount of water which is required. Well, in hydraulic reactions, we know from previous research that the minimum is that the water to binder ratio, this is C because it's water to cement ratio. This was studied for cement, which is a hydraulic material, as you know. So the water to binder ratio shouldn't be lower than 0.4. And also, I need to point out that not just for its hydraulic reactions, water is needed, but also for carbonation, because water needs to solubilize the CO2 for the reaction to occur, and also the calcium hydroxide needs water in order to separate, let's say. So what about, so we have this magic number, which is just in theory though. What about in conservation? What's the binder ratio in conservation? So there are some issues, of course. For grouting, there is evaporation occurring, obviously. There is absorption of the substrate, for example, by the plaster. And we said indeed that in lime pozzolan, there is a hydraulic reaction occurring, but also carbonation is involved, which requires water. So this is just an indication, but of course, we need a bit more water than that, if we think about the minimum we need. So ways to limit water we used. First of all, slaked lime as binder was used. So we're talking about calcium hydroxide, but slaked lime is basically a paste composed of more or less half calcium hydroxide and half water. So we have water here. But what's the good thing about this? That water is adsorbed on the particles of calcium hydroxide. So it's bound through weak electrostatic van der Waals forces. So it's not free water. It's not just the water we add to the grout, which then diffuses through the porosity very easily. It's weakly bound, but still it can participate in the chemical reactions. And then another way to limit water was the use of a solution of water ethanol as a suspension medium, and in particular 15% water and 85% ethanol, so really little amount of water. And this, of course, was achieved at the end after a lot of lab testing with different solutions, water and ethanol. So if I use this solution, what's the outcome? I have a low water content compared to usual grouts, of course. I have a solution which is less effective in terms of solubilizing salts. And I have a lower risk for water-sensitive materials. But what's the point? That if I have the solution which I add to the grout, I have very little water, but in the end, the porosity of my grout will be still very, very high. And so good for my very porous original materials. So these are two grouts, same solid components, different suspension medium. Again, this is a SEM image of a broken section. This is a grout with ethanol, 15% water, 85% ethanol. This is just water. What's the difference? Well, if you don't see much difference, this is great because this is the point. So this is the typical grout just with water. With this kind of alternative suspension medium, of course, balanced, so there is the minimum water amount for the reactions to occur, but still the grout has acceptable properties, good performance characteristics and working properties, and high porosity. Still, all the reactions, chemical reactions are occurring, and indeed, they look very similar because the phases, mineralogical phases formed are very similar. And this was actually confirmed by X-ray powder diffraction, which gives information about mineralogical phases indeed found in materials. And as you can see, there is a very good packing geometry and density for both. So there was a lot of testing of physical mechanical properties. I'm not going to talk about this, of course, today, because that would be too much. But what's the outcome? That water-reduced grout have suitable performance for implementation on site, both working properties and performance characteristics, a very high porosity and good adhesion. And also important to note that ethanol allows carbonation and hydration reactions that was verified, and a significant reduction in water in grouts preparation, as we saw up to 85 for the grout tested, 85% for the grout tested. So the conclusion was that water-reduced injection grout can be useful in the presence of soluble salts contamination and or in case of water-sensitive original materials. And if you're interested, this is a publication with more information. So this is the general approach in terms of injection grout design. And if you're interested, actually this was applied during a conservation project by the Courtauld Institute of Art in Nagaur in India. And this is a publication which is in the IIC preprint. So how do I take my decision in the end? I've done a lot of trials in terms of formulation. I've done a lot of testing. How do I choose? Well, I need to keep in mind the general and site-specific desired properties I have in mind, because there is no perfect grout having all the properties which are amazingly good for my case under consideration. That would be great, but it doesn't really happen. So I really need to keep in mind my requirements, and I need to keep in mind what are the priorities according to the problem. And also it's very important to remember that it's possible, and I would say it's probable, that the grout will behave slightly differently than when tested, because of course you can try to make replicas of your original plaster, but it's never going to be the same. We know that the porosity can be similar, but it's never going to be the same. Of course, there will be no aging because it's a newly produced plaster. And so of course it's very informative, it's highly needed testing, but it may be slightly different when actually implemented then on site. And also we need to remember that also small changes in preparation can lead to a different behavior. So I can't just add a bit more water so that I can inject more easily, because then I need to expect that the behavior will be different. So to conclude, grouting is a complex intervention. Why? Because we saw it's concealed, it's difficult to assess, it's not reversible, and its design can be complicated. It is necessary to tackle the problem with a methodological approach, to have it clear in mind before starting all the different steps and have in mind what we want to achieve. And it's very important that the grout tailors the specific case under consideration. And thank you for your attention.
Thank you, Chiara. Thank you very much for a very informative presentation. Everyone, please keep typing in your questions. So if you're ready, I'll take the questions.
Yeah.
Yeah. So the first question is, could you please talk about a few premixed grouts available that can be used? Which ones can be used?
Sorry, premixed
grouts.
Premixed grouts. Okay. Yeah. So there are a number of them, and I guess according to the countries, we have different ones. I reckon in India you have CTS as well as a company. We have it in Italy, and there is also in Switzerland and in other countries. So a very popular premixed grout by CTS is PLM. And so you can have different kinds according to, you know, lightweight material, particularly lightweight material, or material specifically tailoring plasters or mosaics. So there is a slight change in composition. As I said, not very clear very often. But yeah, they have different kinds. Or in Italy, for example, we have Ledan. There are other German ones. They are mainly hydraulic line based, as I said. There are also some line based ones. I reckon the German ones are. Yeah, so yeah, I mainly know about you know, Italy, Switzerland, Malta, because they use the same ones. And indeed, I know that in India there is the CTS one, but I'm sure there are so many others according to the local suppliers.
Thank you. The other question was regarding the portable microscope. Can you please suggest a particular brand or specific configuration that we should look for?
Okay, so again, there is a variety of them. So there is a particular popular brand, but I don't want to say that it's the best. It's just what I used to use in my previous institutions. It's called Dynolite, but indeed there are many. And of course, you can have more basic ones. They can be very cheap, but still very informative as tools. So they can start from even 100 euros. You can have a decent one. And then, of course, you can have very sophisticated one, and you can have UV light included. But even basic ones are pretty informative, and you can have a quite good magnification already, not being invasive at all, of course, because you just lean on the surface. And so you can have even a magnification of 200 or so. So yeah, even cheap one are actually good. It depends, of course, on the purpose and on the precision and magnification you need.
Thank you. Any other questions? I think everybody's saying very well presented, was very clear. So there are no questions at all, Chiara. I think that's the first. I think the way it was presented personally, I think I really liked it. It's one of the most organized and very well explained talk. So
Thank you.
no questions. Any questions? Please type in. I think it's clear. So
Good. And yeah, you have my email
yeah, we
if
do have
something
an
pops up
email
later.
is there. So if anybody has, they can get in that. Thank you for that. They'll get in touch with you. So yeah, a lot of thank yous and very well done, but unfortunately or fortunately, no questions.
That's fine.
So that just leaves me to say thank you so much. I really enjoyed
Thank you, Padma. Thank you very much for the opportunity. Lovely to be
it.
with
As
you.
you rightly said, now is the time to go. Maybe start preparing your own compositions, do a lot of testing, and then as you suggested. Okay, one question finally, sorry. Adriana, what do you think about props?
What do you think about? Sorry.
Props. Adriana, can you hear me? Can you unmute yourself, please?
I didn't understand. I'm sorry. Props.
Props are useful. Do you think we need props?
Properties.
Maybe. Adriana, can you hear me? If you could just unmute yourself and maybe clarify the question, please. Puntello? No, she's saying Puntello.
Sorry. Yeah, of course. Sorry, I didn't get it. Now I do. Yeah. So, yeah, in terms of implementation. So when the intervention is performed, very often is indeed appropriate to put some presses in order to keep in place the fragile surface while intervening, and so have this kind of props in order to secure the surface. So yeah, definitely useful. Also useful to have a press which is kind of conforming to the surface. So not something very hard, just pressing hard, but something which is, yeah, rather soft, conforming to the surface, and useful to have an absorbent material on top, so on top of the press, so that if there are soluble salts which are mobilized, they can actually be absorbed by the press and removed directly. But yeah, definitely props useful, particularly, of course, when you have ceilings. I would say absolutely necessary when you have ceilings, but also for walls.
Okay, thank you. Andriana says thank you. Any other question very quickly if we can have? Good. I think.
Okay.
And thank you, Chiara. Thank
Thank
you
you.
so much for taking out the time. I know it's been a very busy time for you and given this talk.
For everyone, yeah.
Sure, everyone enjoyed and we've a lot to take away. Thank you everyone for joining us and thank you, Chiara, again.
Thank you. Thanks again, Padma. Goodbye. See you soon.
Goodbye. Yeah.
Bye-bye.
Take care. Bye.